Hello, everyone. So my name is Faith Vowler. I'm the education specialist coming at you today here from Socorro, New Mexico. And also with us today, we have Tyler Cohen, one of our tour guides. And we have Montana Williams, another one of our tour guides. And so Montana, feel free to turn on your screen. Oh, I think for some reason the screen share came undone. My bad. Here we go. And then we also have our operator, Sylvia, who will be joining us later today. And so thank you so much for being here. Today, actually, October 10th, 2020, is the VLA's 40th birthday. So 40 years ago on this date in 1980 was when we first dedicated the Very Large Array and when it was officially open. And we've come a long way since then. And so Tyler's going to tell you a lot more details about the VLA and how it works in a few moments. But first of all, some housekeeping things to get out of the way. So this webinar is going to last about an hour. And if you have any questions that you want to ask us throughout, we'll be doing a few Q&A sessions at different times. We'll do one about any questions you may have about what Tyler talks about, and then we'll be doing a second Q&A session for Sylvia, our operator. And so please submit your questions into the Q&A feature. We are going to be using the chat and throughout, and so we want to make sure that your questions don't get buried in there. We're going to be posting links for things that we'll have several websites throughout the presentation, and so we'll be posting the links in the chat, and we don't want your questions to get buried, so please put them in the Q&A feature. And if you see that the question you want to ask has already been asked by somebody else, instead of resubmitting the same question another time, please just upvote the question. And that way it'll go higher up in the Q&A and we'll be able to see which questions have a lot of people who want to ask them, and we'll be able to prioritize those. So please primarily use, if you have a comment rather than a question, that can go in the chat feature. And also, if you were having any technical difficulties, if you can't hear us or anything like that, you can put that in the chat feature as well. So we also have a poll that we want to ask you that will be popping up momentarily. So we want to know who here has visited the VLA before and who is not, and also where you're coming from today, what part of the world. So we'll give it a few seconds to answer that. And as that poll continues to fill up, then, oops, there we go, sorry. And so you can see here's what the bottom of your Zoom window looks like. So the chat shows you where the chat and the Q&A are if you want to use those. Here we go. And while we will do our best to answer as many questions as we can, it's pretty likely that we're not going to be able to answer all of them. And so if you ask a question and it doesn't get answered during the tour, what you can do instead is go to our website and use our Ask an Astronomer feature. And so there's a whole list of archives of many other questions that people have asked before. So you can search the archives, see if your question's in there. And if it's not, then you can submit a new question, and the answer to that question will be posted most likely within 72 hours. And then we are going to, at a few different times during this presentation, hopefully, if technology works out okay, we will be showing you some videos from our VLA Explorer on our website. So this is a whole series of videos that are usually just a few minutes long that talk more about a lot of different features of the VLA. And so Montana will post that in the chat. And so we're not going to have the chance to show you all of those VLA Explorer videos. So the link is there for if you would like to go check it out on your own. All right, so now we will end the poll here. So it looks like we have about 70% of people who have never been to the VLA before. So that's great. And if you ever do get the chance to visit us, hopefully visit us sometime in the future, once COVID is behind us, then we look forward to having you. And for those of you who have visited before, welcome back virtually. Looks like we have a lot of people coming from North America today, but then we also have some folks from Europe and South America and the Oceania region. So thanks so much for coming. So now I am going to hand this over to Tyler.
Thanks, Faith. Wow, a lot of good questions in the chat already. Yeah, this is the second tour of the day, and a lot of the stuff that I'm going to talk about has been talked about over the course of the day. But if you've joined us late or you caught the tail end of some of the talks, this might give a little context to that. So here at the VLA, astronomers are interested in studying radio frequency light from space. Throughout this discussion, and probably throughout, if you've been here throughout the day, you've heard the word frequency a lot. Frequency is the word that astronomers use to refer to the energy that light has. High frequency means high energy. Ultraviolet light, the kind that comes from the sun, it can give you skin cancer. It's high frequency, it's high energy. Radio frequency light, the kind we look at here at the VLA, is low frequency, it's low energy. In fact, it is so low energy that if you were to add up all of the energy of the radio light collected by the VLA since it began taking data 40 years ago in 1980, it would amount to less than that of a snowflake hitting the ground. I'm not making that up, I've done the math, it is absolutely true. So low energy, but contains a wealth of information. And for thousands of years, humans only had access to a narrow range of the full spectrum of energies that light can have. We look only at visible light, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet with our puny human eyeballs. If you make the analogy between sound waves and electromagnetic light waves, the range of frequencies on a standard piano keyboard in a single octave is comparable to the range of frequencies that are visible to the human eye, visible light. And so the light that we can see with our eyes, if that takes up one octave on a piano keyboard, the entire spectrum of energies, of frequencies that light can have would fill more than 50 octaves on the piano keyboards, just to give you an idea of how limited our vision is in the scheme of what exists to be discovered and what is emitting light in the universe. And it wasn't until the early 20th century that the first radio astronomers began to understand this huge window onto the universe previously beyond our vision. So that's what the National Radio Astronomy Observatory, or NRAO, was established in 1956 to do, was to open our eyes to the lowest frequencies, the lowest energies of light that we couldn't see without radio telescopes. There we go. So the NRAO consists of 3 radio observatories. Obviously, one of them is our beloved VLA. Happy birthday, VLA. Our Southern Hemisphere sister observatory is called the Atacama Large Millimeter Array, or ALMA. It's not ALMA. Go back. It'll catch up with me. Made up of 66 radio dishes located in the high desert of Chile, ALMA picks up where the VLA leaves off, both in its coverage of the southern sky and in frequency coverage. While the VLA can observe light with frequencies of about 1 to 50 gigahertz, ALMA can observe radio light from 85 gigahertz to almost 1,000 gigahertz. Now, the third observatory that comprises the National Radio Astronomy Observatory is the Very Long Baseline Array, or VLBA. 10 VLA-sized dishes that span the North American continent from Hawaii to St. Croix and the Virgin Islands. And there is a lag with this presentation. There we go, that's the Very Long Baseline Array. Hawaii to St. Croix and the Virgin Islands. New Mexico is the only state to host 2 of them. We've got one in Pie Town, just west of the VLA, and another one up north in Los Alamos. But let's give the VLA the attention it deserves on its birthday. So why are we here? Why build one of the world's premier telescopes in the middle of the desert? Well, the plains of San Agustin were specifically chosen as the site of the VLA for a few reasons. Population density here is relatively low, which means fewer sources of radio frequency interference, which are unwanted radio waves from terrestrial sources like cell towers, Bluetooth, and radar, or from other technology like satellites. And we're shielded by the surrounding mountains. Now, of course, we still have to contend with the radio world that we live in. You know, there's cell tower on the hills that's just above Magdalena, and people drive by on Route 60 with Bluetooth turned on in their cars. But there are far fewer sources of interference out on the plains of San Agustin than if we were to build our array near a city like, say, Albuquerque. Also, the plains here are relatively flat. We are, after all, situated in a prehistoric lake bed, which makes it really easy to move your radio dishes to different locations, which is exactly what we do here. Now, while this wasn't a consideration when the VLA was first built, it's also a relatively arid environment, and the lack of moisture in the atmosphere is great for high-frequency observations where water molecules can actually change the path that light takes on its way to our telescopes. Now, the VLA wasn't originally designed to go up to these frequencies, but it turned out to be a great thing that we are in a dry climate here for those higher frequency observations. Now, the VLA began construction in 1972 and was completed and began taking data in October of 1980. Yes, the VLA turns 40 years old this month. In the early 2000s, the VLA was in desperate need of an upgrade. In 2001, we received money from the National Science Foundation to upgrade the VLA to what we now call the Expanded VLA, or EVLA. The waveguides that carry the signal from the antennas to our correlating supercomputer were replaced with fiber optics, and the correlator itself was upgraded. This expanded the computing power, expanded the bandwidth that we were capable of processing at a given time. And this was completed in 2012, and the telescope was rededicated for one of the founders of radio astronomy, Carl G. Jansky. Now, Dave Finley gave a much more detailed history of the VLA and its contributions to radio astronomy this morning, and that talk will be available on our Vimeo page in the next couple weeks. And now astronomers at NRA are looking forward to what's next for the VLA, and we are very excited about the prospect of a next generation VLA, or NGVLA. It's a proposed instrument for which we've received research and development funding from the National Science Foundation that has the potential to revolutionize the field of radio astronomy. This instrument would be comprised of over 200 stationary 18-meter dishes spread across the state of New Mexico and potentially into Arizona, Texas, and Mexico. It would almost double our frequency coverage and offer greater sensitivity to faint astronomical sources than any other radio telescope on the planet. Suffice to say, we're very excited, and we will find out if the project will be funded sometime next year. Now, if it is funded, construction would begin around 2025 and be completed in 2034. And if you want to learn more about the next big thing in radio astronomy, you should check out the recording of Rob Salinas' talk from earlier in the day, which will also be available online if you missed it. Now, the VLA is made up of 28 radio dishes that are 25 meters across and weigh over 200 tons each. These dishes are laid out in a Y configuration at discrete locations along over 80 miles of railroad track, which allows us to move the dishes to different locations. Now, there are 4 main configurations that the dishes can be placed into. In the D configuration, the dishes are darn close together. Come on, presentation, there we go. D for darn close together. In this configuration, the furthest dish is only about a mile from the center of the array. And the next widest configuration is C, then B, and then A, where the dishes are a long way away. In A configuration, the east and west arms are 13 miles long and the north arm is 11 miles long. Why are they different sizes? Well, there's a ravine at the top of the north arm that was too difficult to build over, so that's where it stops. And right now we are in the B configuration. For the next 5 years, we will have a special 5th configuration, which is a hybrid of the B and A configurations, and which we will move into at the end of this month. We call it B North A. The east and west arms are in the B configuration, while the north arm is in the A configuration, which gives us increased sensitivity toward the galactic plane, on the southern horizon for a special project called the VLA Sky Survey, or VLAS. This is a project to map the entire radio sky visible to the VLA at frequencies from 2 to 3 gigahertz in order to provide the astronomy community with a catalog of radio sources of the sky across the light spectrum. Now, if you visit the VLAS website, it's right here. You can also post that in the chat. If you visit the VLAS website, you can view the regions of the sky that they've mapped so far. Now, Amy Kimball gave a great talk about VLAS earlier, and that'll be online as well if you want to know more. Now, before we added this hybrid configuration, we would normally change between configurations every 4 months so that each configuration would fall on a different part of the year every year, giving VLA users access to the greatest variety of targets. Now, depending on weather conditions, the current configuration, changing between configurations can take anywhere from a few days to a few weeks. In order to change between configurations, we have 2 big red diesel engines, which have hydraulics to lift the antennas and move them at a blistering 2 miles per hour to carry them to their new location. They have to move slowly because the antennae are not bolted down during the move, and the dishes can act as sails if wind speeds get too high, and we don't want to find our antenna tumbling across Route 60. So here's project scientist for the EVLA, Rick Perley, to explain a little bit more about the transporters.
So now we're going to go up into the end. So every 4 months, the array is reconfigured, which means that transporters are used to pick up some of the antennas and move them to different pads. This is one of our 2 transporters. It's a unique machine. It comprises 4 trucks of 6 wheels each. I'll explain in a moment how we actually turn corners with this. The basic idea of this machine is pretty straightforward. You see the flat deck on there. The transporter moves down the rails, slides underneath the antenna. The antenna is then unbolted from the 3 concrete piers on which it normally sits. The transporter is raised up on hydraulic jacks, lifting the antenna up about 6 inches, enough to clear the bolts, and the transporter then backs up and takes the antenna to the main line. Now, the way the antenna transporter turns a corner is quite unusual for a rail vehicle. The engineers invented this right-angled turning system, which works in the following way. The transporter moves over the main line, and this is the main line heading down, say, towards the center of the array. It's a double track. The transporter trucks are each over the 4 intersections of the 2 double tracks. A hydraulic jack lifts up one side of the transporter 3 or 4 inches, just enough to clear the flanges of the 12 wheels on one side. The 2 trucks of 6 wheels each on that one side are then rotated by 90 degrees and put back down again. The other side of the transporter is then raised 2 or 3 inches. The other 2 trucks are rotated 90 degrees, and the whole assembly rolls off in a 90-degree different direction. So the
Rick? Are you there, Rick?
Nope, it's back to you, Tyler.
Oh, was that the end of Rick?
Yeah, it's back to you. Yep.
Okay.
Yeah, it was just part of that video.
I can't go back. I want to go back. All right, great, thanks. During a change in configuration, we are still observing. We have a rule which we call the 3 antenna rule, which means we can have as many as 3 antennae not doing science and still get the quality of data necessary to satisfy our astronomers. Now, the reason we change configurations is because it allows us to change our sensitivity to scale. It may seem counterintuitive, But in the D configuration, we have the lowest resolution and are sensitive to the most diffuse structures, like the woofly lobes of a jet from an active galaxy. In the A configuration, we have the highest resolution and are sensitive to the supermassive black hole at the center of such a galaxy, or the circumstellar disk of gas and dust in an infant solar system. Now here at the VLA and at ALMA and the VLBA, we are using a combination of smaller, discrete dishes to synthesize a telescope bigger than one we could physically engineer. The way that we do that is by combining the data from the individual antennae using our correlating supercomputer. It's a supercomputer in the sense that it can do one thing very, very quickly, and that's multiplication. It can't play Fortnite, but it can do 1 trillion multiplications per second. And the way that it does this is by multiplying the signal from antenna 1 by the signal from antenna 2, and the signal from antenna 1 by the signal from antenna 3, 4, 5, 6, all the way up to 27, and the signal from antenna 2 by the signal from antenna 3, and 4, 5, 6, all the way. You get it, so on and so forth. And that gives us 351 pairs of antennae that we call baselines. These baselines are what allow us to reconstruct an image of the sky as if we had a single 20 mile diameter telescope. Now, each VLA dish contains 8 receivers at the vertex, which cover the frequency range from 1 to 50 gigahertz, and 2 feed systems just below the prime focus on the apex of the antenna, which cover the really low frequencies from 58 megahertz to 470 megahertz. Now, each of the receivers at the apex of the antenna has a feed horn to go along with it. And I meant to show this on the earlier tour, but I forgot to. I have a VLA feed horn here with me. Dan Mertley, if you're watching, I promise I'm still using this for something, actually. I'm not just holding onto it as a cool paperweight. But this is really what we mean when we say antenna, when we talk about the VLA. The dish is not so much of an antenna as this is really an antenna. And perhaps if I hold it close enough, you can see down here at the very bottom of this, there is a little needle, and that is really the antenna. This is what couples the electromagnetic radiation that we are receiving from space to an actual transmission line, to an actual current in a waveguide or in a fiber optic cable. And these have to be designed very carefully because you don't want to be collecting radiation from unintended directions that can increase your sensitivity to RFI. But those are a very vital component of the observing system. And here is Rick Perley to tell us a little bit more about the VLA receivers.
Now we're going to go up into the antenna surface. I've done that so many times, it's second nature. So in a cone to go. One thing more that needs to be done for safety. And up we go. I've done that so many times, it's second nature. So this is a 25-meter paraboloid, and the paraboloid works the same way for all. The radiation comes in from the direction the antenna is pointing, strikes the surface. In this case, it runs up to that subreflector, that conical-shaped, asymmetric subreflector. And from there, the radiation is down in a cone to go in one of the 8 feeds. We change our frequency by rotating the subreflector. So these feeds are not on the optical axis of the antenna, but they're arranged around a ring called the feed ring. And we can illuminate any one of them at a time. So that's the reason why we normally can observe only in one wave band or one receiver band at a time. So the 8 horns that you can see there, they're all different sizes. The larger the size, the longer the wavelength. So the big one is what we call L band, 1 to 2 gigahertz. That's 30 to 15 centimeters radiation, which goes into that horn by appropriate rotation of that subreflector. If we're interested in 2 to 4 gigahertz radiation, then the subreflector is rotated by 180 degrees and the radiation goes down that second largest feed horn called S band. And so on and so forth with the other 6 receiver bands By appropriate rotation of the subreflector, the radiation from the direction we're interested in will go down through the horn and into the receivers. Each of these horns is covered with this white window material. This is for weather purposes. It's not necessary for the function of the horn. This is to keep rain and snow and dew, bird droppings, and everything else out of these horns. There's a little bit of loss associated with that, but that's just something you have to accept. The funny inverted shape objects that are above the smaller horns are all heat lamps. We don't want dew or frost forming on the surfaces, especially at the higher frequencies or the shorter wavelengths. So when the dew point and the temperature are close together and sufficiently low for us to determine that dew is forming, the computer recognizes these combination of conditions, turns on these heat lamps, which warms up the surface and prevents frost and dew from condensing on top of these weather windows.
Thank you, Rick. Yeah, somebody said in the chat that they couldn't see the antenna when I was holding it up. Maybe that's because we're in presentation mode and my my actual video panel is small. So I'll show it again in the Q&A session. Alrighty, so you might be wondering who can use this incredible telescope. So if you don't mind, take a moment to fill out a quick poll on who it is you think can use the VLA. We have the results of the poll. No. So do you think that you are eligible to observe with the VLA? If you want to, the yeses are correct. You can, no joke, this is a taxpayer-funded observatory, which means that anybody with any background in any country in the world can use the VLA. You just have to write a proposal. There's always a catch. You have to write a proposal where you demonstrate that you understand the capabilities of this instrument and the science that you want to do with the VLA. And that the science that you want to do has the potential to benefit the scientific community and advance our understanding of the universe. A panel of NRAO scientists review all of the proposals. I think it's twice a year for the VLA and once a year for the VLBA, and award telescope time based on the merit of the proposals. And we've awarded high school students observing time with the VLA, and every summer we have undergraduate college student interns who are given director's discretionary time on both the VLA and VLBA. So you do not have to be a tenured professor in order to use it. And we typically oversubscribe the telescope because we don't want any downtime. So we'll award around 4 times the amount of telescope time that we actually have available. Now, proposals are given a ranking where A, priority is the highest and means we'll try as hard as we can to run your observation. And the lowest, C, is basically filler time if the conditions are too poor for a high priority or if there's gaps in the schedule. So if you are awarded time on the VLA, you'll then work with one of our data analysts to write a script, which is a set of computer instructions that automatically tells the dishes how to move and when and where. Then our script goes into queue, and our schedulers and algorithms arrange the observations based on the time of day and year, which targets are above the horizon, and by the configuration that we're currently in and by weather considerations like wind speed. This is called dynamic scheduling, as opposed to fixed scheduling, which we did for roughly the first 30 years of VLA operation, where your observation is scheduled for a specific day at a specific time, and if something goes wrong, you're out of luck. But ultimately, the operators make the final decision on which observations get run, and you'll get a chance to ask Sylvia, one of our operators, questions in a few minutes. So once your data is taken, within minutes, it's sent to our offices in Socorro. Where it's checked by our data analysts, who are our last line of defense to ensure that the data is of the highest quality before it gets sent to the astronomers who proposed for it. And once it's sent to the astronomers, they own those data. It's proprietary for 1 year, and those astronomers can do their analysis and write their journal papers without anyone else seeing. But after that 1 year, that data goes into a public archive, and it's fair game for anyone who wants to use it. So all of the data ever collected by the VLA that's older than 1 year is publicly available on our website. So even if you weren't awarded time on the VLA, you can still look in the archives and see if someone in the past observed what you're interested in, and maybe they missed something. That's one of the great benefits of publicly funded science. So before we start the operator Q&A, let's take a few minutes to answer some questions that you might have from this past presentation.
Thanks, Tyler. And so one question that we have, and this is definitely one that we get a lot, is so the introduction, this person's introduction to the VLA was from watching Contact. And so is there anything during the film, like during the scenes at the VLA, that the staff would like to set the record straight on? And the answer is definitely yes. So two big misconceptions that movie can give you. It's a great movie, but for one thing, we don't directly use VLA data here at NRAO for the purpose of SETI research. So we do have an arrangement with SETI where they can take data that our antennas receive and use that for their own research. But at the VLA specifically, we are not conducting SETI research. So our antennas are really good for zooming in on a particular object out in space and taking a really good look at it. When it comes to searching for extraterrestrial life, we don't know where we're going to find that. So to do those kinds of searches, we would want to telescopes that primarily just scan the sky most of the time, just pointing at lots of different things. Whereas when we use the VLA, the places that we point it, we have a specific reason for looking at that object. And then the other major misconception that gives you is there's the very famous scene where Jodie Foster is wearing those big headphones over her ears because she's listening to the data that they're receiving from space. So we don't listen to the VLA data that we receive, we look at it. In theory, we could listen to it, but in practice, we don't, because that's not really the most efficient way to understand the information we're receiving. So these dishes receive radio light from space, and that's a type of light that our eyes are not able to see, as mentioned earlier. And so we instead convert that light into pictures using colors that our eyes are able to see. And so in the same way that the radio in your car converts radio light that it receives from a station into sound, we could do the same thing. But again, we're going to have a much better understanding of the data that we're getting from space if we look at it in the form of pictures as opposed to trying to listen to it. Okay, so
Henry, I got a good one. Henry Paul Kowalski, any relation to Sylvia, asks, again, did I see a J-pole antenna above the dish? What is its purpose? That's a great question and an excellent eye, Henry. Yes, so there are 8 receivers at the vertex of the antennas, but we also have 2 feed systems just below the prime focus underneath the apex of the antennas where the fork arms meet. we have our low frequency feed systems up there. So I said before that the VLA goes from 1 to 50 gigahertz, but actually we can go a little bit lower than that. We can go down to about 50 megahertz. And so that's what, there's actually two feed systems there. There's that edge-fed, an end-fed J-pole feed system, which kind of goes around the corners of the fork arms. And there's also just below the secondary reflector, which is underneath the fork arms, there is a center-fed dipole there as well. And so those are the two feed systems that that we use to observe from 50 to about 450 megahertz.
And then another good question that we have, where I'm going to save part of it until when we get into our operator Q&A, but to start on it now. So it's, what kind of background do you need to understand how the VLA works? And that honestly depends on like what you're doing at the VLA as an employee, because we have people who work in all sorts of different areas. We have our cryogenics experts who like worry about the stuff that we put inside the antennas to keep the receivers cool. We have our electronics experts. We have the mechanics who service the antennas and we have the track crew who moves the antennas up and down these railways into the different configurations. We of course have the astronomers who do research. We have the education folks like us, and we don't have to have necessarily huge in-depth ideas of a lot of things, but we need to have a general idea of many different aspects of the VLA. And then when we get into our Q&A session with Sylvia, then she can tell you the kinds of things that an operator needs to know. Okay.
This is kind of in line with there's just another similar question that Andrew asked, which is what types and levels of mathematics does an operator or astronomer at the VLA use on a regular basis? And I can answer this a little bit for myself, but I'm sure Sylvia can answer this as well, and it might be a different set of math skills. I tend to use a lot of linear algebra, definitely a lot of statistics. Really, if you're doing any kind of astronomy, you have to have a very, very, very strong command of statistics concepts, because that's what allows you to understand. I mean, the fundamentals of radio astronomy are based on principles in statistics, things about probability distributions and central limit theorem and things like that are fundamental to the fact that radio astronomy even works at all. So maybe Sylvia has some different answers to that, but I would say, at least for myself, certainly linear algebra and statistics.
Okay, so I think with the rest of the questions we have, we can continue those into the operator Q&A. So now we are going to welcome our operator on duty, Sylvia Kowalski. So the operators out at the site do a lot of different things. And also, Sylvia, you're welcome to come on camera and say hi whenever you're ready to. So.
Great, thank you so much, Faith. I forgot that we were using that picture of me wearing an antenna hat. I really like it. Hello world, thank you so much for coming to celebrate the 40th birthday of the VLA. Okay, go ahead, Faith.
Yeah, so the operators, as you can see here, they have a lot of different computers they have to monitor. Actually, I have another video I can show you that shows the control rooms, so bear with me just a second here. Luckily, the videos have been working better.
Yay.
The very large array is controlled from here in this room on the top floor of the back of the control building. As a radio telescope, the VLA works night and day. The array averages 5,000 hours of observing every year, with maintenance and reconfiguration scheduled in between. All activities are directed, controlled, and monitored by staff in this control room.
All right, so now back to our presentation here. Yes, so the operators are pretty much the VIPs when it comes to being on site, because they kind of act as the site managers in a lot of different ways. So during our weekdays, we frequently have our antenna crews going out onto the antennas to perform maintenance on them. And when they're doing that, they have to coordinate with the operators before, during, and after that process. And they also look out for the safety of everybody on site. So if there's, for example, wildlife in places where it shouldn't be, they would call the proper person on site depending on the time of day to have them come and relocate that wildlife to somewhere safer. If there's a thunder lightning storm going on, then they'll let everyone know to please come inside for their own safety. If we're going to have a tour group on our site, obviously during non-COVID times, we let the operators know about that. And we have security on site every day. And so the guards also coordinate with the operators as well. So they are very important people. And so we have somebody on site 24 hours a day, 7 days a week, 363 days a year, or since this is a leap year, 364 days. All of the operators get Thanksgiving and Christmas off. So, hooray. But then we do have somebody present at all times. So the day out at the site is split into 3 different 8-hour shifts. There's the day shift of 8 a.m. to 4 p.m., the evening shift of 4 p.m. to midnight, and the graveyard shift of midnight to 8 a.m. And operators actually start their day here at our office building in Socorro, and then they drive an hour out to the VLA site, work there for 8 hours or a little bit more, and then they spend another hour driving back. So they work 10-hour days, which also means that they only have to work 4 days a week, so they get more days off. So I've gathered that they tend to like that pretty well. And they generally cycle with who does what shifts, except for there's one fine gentleman out there who always does midnight shifts.
Yes, thank you, Sam.
All right, so Sylvia, do you want to tell us a little bit about your background?
Yes, of course. I would love to. Also, Faith, I feel like every time I hear your spiel about my job, I like remember something else that I do. So thank you. But yeah, so my background, I grew up in Seattle, Washington, a lot cooler and a lot cloudier than New Mexico. And I was first intrigued by astronomy from actually a high school course in astronomy. That inspired me to pursue a bachelor's degree at the University of Washington in astronomy and also physics. So I have a BS in astronomy and physics. But I was and still am a theater nerd. So I also have a Bachelor of Arts degree in drama. And during my time at the University of Washington, I learned that while I loved using astronomical data to make discoveries, I really liked working with the telescopes and the instruments themselves even more. So that's what I decided. I wanted my path to explore more the instrumentation and the ingenuity that it takes for astronomers to collect this light from space, which really is like one of the only tools that we have to learn about the cosmos. But at the same time, I also discovered while working at a science museum in Seattle, the Pacific Science Center, that I really love science education and outreach. So those have kind of been the two paths that I've been pursuing since I graduated. I have worked at the VLA for about 2.5 years now. My official job title is Operations Specialist 2, but we typically just call ourselves telescope operators. Like Faith said, our job is sometimes really all over the place. It's really very varied. So when we come into work, not only are we rotating between these shifts that can be very different, we really have no idea what's going to happen on any given day. And I love that because I love it when my day is really exciting. It could be maybe it's a midnight shift and all of the observations that I pick to run with the current weather conditions run perfectly, and I just get to enjoy being a part of this amazing scientific process of learning about the cosmos. Or maybe it's a maintenance day and there's 50 million people calling me on the phone and the radio, and I need to fix things on the telescope with my software, and it's simply bananas. So it really to be an operator, I would say we're looking for people who both have an excitement about a technical engineering instrumentation side, but are also really comfortable with dealing with a lot of people, managing situations that are maybe high stress, really time sensitive. So that's kind of the skills that we look for in candidates for telescope operators.
Awesome. Thank you. So now we are going to move into our Q&A with Sylvia. And so one of the questions from earlier was, so what kind of things do you need to know, like background do you need to have specifically for your job? And then there's also a pretty similar question, just like it can be educational and job background, like special skill sets, just that general thing.
Yeah, those are really good questions. So for an operator, a lot of what we're doing, we're monitoring, maybe not during like a maintenance day when we're doing a lot of people management, but maybe it's a shift where we're entirely running science observations for astronomers from around the world. A lot of what we're doing during that type of shift is that we're monitoring all of the antennas and their subsystems. In order to do that correctly, we have to have a pretty in-depth knowledge of how each of the subsystems of the antenna works so that we can notice if something is going wrong, how it's going wrong, and maybe a potential solution for it. And then we have a toolbox, not a physical toolbox, but an intellectual toolbox to solve a portion of these problems. But of course, if it's a really large problem that arises during a shift, we will probably be calling someone and waking them up at 3 a.m. to help us try and figure out, what's going on. But I would say that's one of the main things, is understanding the electronics and the hardware of this system. Like Tyler said, a lot of the theory that goes into making radio astronomy work is statistics. So we're using a fair amount of basic statistics. And then when we are monitoring a lot of this data, we're looking at numbers and we're also looking at graphs. So the ability to read a graph that's expressed in different types of units and understanding enough of the physics and astronomy that's happening to really be able to take, this data that we're seeing and kind of understand what could be going right or wrong during that time. Like I said, I have a Bachelor's of Science in Physics and Astronomy. We have a fair amount of operators that also have bachelor's degrees in physics or math or astronomy. We also have some folks who have a background in electronics and engineering. So that's kind of the background that we're looking for. And I think there was the follow-up question about maybe just some other skills that are important. Like I said, our job can sometimes be really chaotic. So having a personality where you're pretty comfortable with things getting really wild and staying calm even during chaos, I think is a really important quality. And then also maybe one more thing is that I think you have to be really passionate about what we're doing, because there's a lot of things that are strange about our job. We're working all hours of the day. You never know what your day is going to be like. There's a lot of driving involved. So I think a passion for the science and this quest to learn about the universe, I think, is really important. And all of our operators have that to such an incredible degree. So it's just an awesome team to work for.
Yeah. And then someone asked, is Sylvia both operating the VLA and talking to us right now?
Oh,
See, this is an advantage of the virtual format, because if we
Great
were in
question.
person, the answer would be yes.
that is true. And if, and like Faith said, if it was a public tour, I would be talking to you, but every like 5 minutes, I'd be like, okay, let me just check all my stuff. Okay, hello, let me just check. So it is really, I will say, it's really nice. I am not the operator on duty right now. It is 4:21 New Mexico time. So right now we have an afternoon operator is working. I don't know who's operating right now. Hannah was the day shift operator, I think. Whoever's operating the VLA right now, thank you so much. But no, I'm sitting in an office in our Socorro office building right now.
Great. And okay, so this is also kind of on a similar note, but what would be the next career steps for someone who's an operator? Like, you're an operator now, in the future, what kind of careers might you move on to?
That is a really good question. It really depends on the person. We have had excuse me, telescope operators who absolutely love everything that goes into being an operator, and they've worked at the VLA as an operator for over 15, 20 years. There's some people that realize the rotating work shifts and some of the up-down stress, how it's so varied, is not really their jam, but they're really still interested in working maybe with data that comes from the VLA. So we've had people who work for a while as an operator and then maybe shift into a position as maybe a data analyst or a scheduler, such as Melissa is a data analyst, so working with the data after it's come through the telescopes. I think one benefit of being an operator at any telescope is that you really have a pretty intimate understanding of the instrument. So if you want to move around within the observatory, you are coming in with a pretty substantial body of knowledge about how this instrument works. So again, it's really up to the operator.
Nice. And then related to that, how many years do operators typically stay at the VLA? I'm assuming that probably varies too.
It definitely varies. Though I will say we tend to see, it's kind of bimodal. We see people who stay like 1 to 2 years, and then people who stay like 5 to 20 years. So you try it out and you either love it, or you try it out and you say, that was awesome, but I need something else. So it's really varied. Yeah, again, like I said, I've been working here for about 2.5 years, and it's absolutely awesome. We have a couple of operators who've been with us maybe about a year now, and then some more than 10 years.
Right.
Yeah.
And then examples of chaos up on the hill during your shift. This is kind of a two-parter, so that's the first one. Like, what are some chaotic things that happen during your shift?
That's a really good question. So I'd say probably the most chaotic and things that maybe happen most often are any instances with power. So, if you're in your house and there's like a little power glitch and the lights flicker, but everything comes back on. If you're at the VLA and there's a power glitch like that, a lot of our subsystems, if there is a power glitch where they get turned off and then back on again, they're no longer synchronized with this very, very exact timing that we have to keep. So it can wreak a ton of havoc, even just a little glitch. So things related to power are probably the biggest. I've kind of been trained emotionally, even if I'm just in my house and the lights flicker, I get a rush of adrenaline, and inside my head I'm thinking, okay, what do I need to fix? So that's probably the biggest. And then of course, anything that's related to like an emergency situation, as we are, the control room is the only room that has someone in 24/7. We are in charge of managing both routine situations at the VLA, but also emergency situations, like Faith and Tyler said. So anytime we're dealing with the health and safety of a person, the health and safety of a hardware component or antenna, that's really stressful, and that can be really difficult. And then sometimes just really, bizarre things. We had, Faith reminded me earlier today, there was a day that was really windy. We had some gusts that were up to about 60 miles per hour, and one of the panels that's covering that main dish came off of the antenna, and that's not something that we'd ever seen before. So every single day at the VLA or night, there's going to be something new that happens.
That was a
and
great time.
it was so bananas, and the picture kind of looked like the antenna had lost a tooth. It was super, super goofy. So yeah, I think those are probably the emergency situations, and power are definitely like the wildest.
And then as like the second part of that question, do you get full 30-minute lunch breaks and 15-minute coffee breaks?
Oh, that is such a good question. Not in the traditional sense where you're like, oh, it's been 4 hours, I'm gonna go take a lunch. We take our breaks and we rest our mind when the VLA is calm. So if VLA is not having a good day and there's a lot happening, your day is not very restful. But if things are calm, that's great, and you can leisurely enjoy your lunch while sitting in front of all of your monitors in the control room. We try to ensure that the longest break, so the long amount of time that an operator is away from the control room, is 4 minutes and 59 seconds. So if you got to go fill up your coffee cup or go to the bathroom, just make sure it's pretty speedy, and take your allotted breaks when things are calm. Great question.
Yeah, makes sense. And then what's the data rate for the scanning functions? Do you know?
Oh, that's such a good question. And I will admit, we look at that and right now I cannot remember the number. But I will say it really does change depending on the observation. So kind of related to that, one of the components that's going to go into the data rate and how much data we're storing for each observation is going to be the length of the observation. And that can vary tremendously. So if, let's say, Faith, you were awarded 20 hours of VLA observing time, congratulations. You can work with the data analyst to create a script that is either 20 hours long, or you could chunk it up into different amounts of time depending on the science that you're doing. Typically, we will observe what are called scheduling blocks, which are either components of an observation or the entirety of an observation. And they typically range from about 1 to 3 hours in time. So after that, after that one observation was run, we have to make sure to have the next one queued up and ready to go, because at most we want to have 1 second between the time that one observation ends and the next one begins. We have so much science to get to. We have to be very, very speedy with that.
And then someone asked if they have pictures of the control room that we work in. So that's mainly the pictures that we have here. So I'll go back a couple of slides. So this basically is the control room. This is Sylvia in her natural habitat at work. And,
yes, I feel at home.
And then from the video too, that was basically, so this, what you're seeing here in these pictures is the control room out at the site.
Yeah.
And then a question, we're getting a lot of questions from people named Kowalski today. So what kind
that
of
is
effect?
Definitely my dad. Hi, Dad.
What kind of effect does space junk have on your work?
Oh, that's a really good question. Space junk. Well, I would say, at least as an operator, we're more interested in the stuff that humans put up in space that are working. So as we've been saying, satellites, things that are broadcasting radio light down to Earth for all of the things that we need it for, radio stations and entertainment and Wi-Fi and cell phone service. Those are really, those are the buggers, because they're blaring this really bright radio light, and we're trying to see through that and see the really, really dim sources of actual cosmic radio light. So for the most part, the things that humans make that are still working, That's going to be the big problem. Other kind of junk and stuff floating in space. Maybe an astronomer wants to study that. That's a great question.
And then I think we have time for one more. So is there anyone who's been there since the beginning? And
That is a great question. Yes. Yes, we have quite a few amazing people who have been with us since the beginning. I feel like we should also give them some sort of mega award today for helping VLA get to 40 years, which again, I'm amazed that an instrument, because technology is evolving, but we've figured out ways to upgrade our instrument as technology evolves. So I think that's just, a testament to these people who have been here for 40 plus years. They're part of the reason we are able to even celebrate today.
Yeah, and it is 40 plus because they didn't just come here right when the VLA was dedicated in 1980. We started building it in the 70s. So in terms of how long they would have been here, that's longer than 40 years. And for some of them, their various jobs have changed, but it definitely is like, meanwhile, I've just been here 3 years. So it's great to hear all sorts of really cool, interesting stories from people who have been here for either the whole time or for a very long time at least, and all the great stuff they have to say.
Yeah, that's a really good point, Faith.
Yeah, one of the people who's been here the whole time was Rick Perley, who was the guy in those couple of videos that I showed you early on in the presentation.
Yeah, thank you. Yeah. Faith, I just had one thing that's not really related to anything technical that I forgot to share in the first tour, and I really wanted to. I don't know if other telescope operators experience this, but I dream about the telescopes all the time. Sometimes they're like super stress dreams where like I realize that an antenna has fallen over or the control room has been completely reconfigured and I don't know where any of my monitors are and it's really stressful. But sometimes the dreams are amazing. Like there was this one time where I dreamt that I found a 29th antenna somewhere in the woods.
That is awesome.
It was so goofy. So, yes, the VLA is very powerful and it infiltrates my mind when I sleep.
I'd imagine, the stress dreams would be like kind of in the vein of the, oh my God, I forgot to do my homework sort of thing.
Yes. It's
level of stress, but that's great that you dream about things like finding a 29th antenna too. I love that.
It was so goofy. And I think in my dream, I remember thinking, I hope I get a really big raise for this.
Yeah, if you found a 29th antenna, I think you would deserve one at that point.
Thank you. Thank you so much. Awesome.
All right, well, that's the end of our presentation today. So everybody who wants to can come back on and say goodbye, but thank you so much for being here today. And so if you want more VLA, we also on our website, we have the webcam that you can look at that shows you live footage from the VLA right now, and the VLA mission control, which likewise shows you what the VLA is currently observing. And our next virtual tour is going to be in about a month on Saturday, November 7th, and that will be 1 to 2 p.m. Mountain Standard Time. And so thank you so much, everybody, for coming today. This has been a great 40th birthday for the VLA, and have a good one, everyone.